Hello, this is my computer science NEA proof of concept, which includes some perceptrons for neural networking, as well as a proof of concept of the design and playability of the ball. So the first thing I did was work on a single layer perceptron, and this was to try and solve the XOR problem. So we have here the training data, which is a 2x4 grid array, and the target outputs, we have the XOR target, as well as 3 other possible gates, a NAND or an AND gate. Here we create our perceptron, including the initialization variables, the training data, the target data, and the learning rate. We also have 2 input nodes. We have the gradient, which is key to try and figure if it's correct. And we have the updating of the weights, which is telling us if it is correct or not, and if we need to change it. This is running it forward through the perceptron. And this is telling us whether the data point is correct or not. This is creating a plot, an invisible graph basically, telling us if our point's from the correct location. This is the decision boundary. And this is the main training section. So while training, first we set the correct counter to 0. If this hits 4, that means it is correct and is fully trained. Anything less than that, and it's not. For example, a value of 3 would show that it got the 3 out of the 4 correct and then was wrong, so it starts again. So with the single layer perceptron, if we try and run it with, for example, a simple AND gate, the output will be the terminal at the bottom. I just trained it, so it's going to get it correct first try. So let me quickly change that to a different type of gate. For example, an OR gate. As you can see, it solved an OR gate relatively, well, instantaneously for us, but very quickly in terms of time and outputs. As you can see here, not long at all. However, if we try and actually do a XOR gate with a single layer perceptron, we can see it simply cannot, as it is too complex. It's a combination of 2 gates, and a single perceptron cannot solve it. That's what this repeating 0 here is showing. So, logically, the next step, we'll go to a multi-layer perceptron. The multi-layer perceptron is similar to the original perceptron, but this time it also has a hidden layer, and the hidden layer allows it to take more inputs and have more outputs and decisions. The key thing here is back propagation. When updating the weights, it takes into account the previous error and how close it was to the right result, which lets us know how close it is and can on the fly update itself to become more accurate, whereas the single layer perceptron can't do this as accurately. For this, we're going to need a sigmoid curve, a sigmoid graph, as you can see by the sigmoid function that is repeated around quite a lot. So this is the hidden layer, this is the output layer, and this is updating the weights. As we can see, the learning rate multiplied by the gradient and concluding the backpropagation. This is the sigmoid graph, this is the function. There's an image of these all in my document. This is very similar to the previous one. This is once again plotting a decision boundary, and this is once again training it. So, if we were to run this multi-layer perceptron with the training data, a target XOR, and the learning rate of 0.2, and we're going to run, let's go with 3,000 epochs here. So it's going to run 3,000 times. I'm going to get quite a lot of outputs. As this should be getting closer to 0, I believe. As you can see at the end, it's incredibly small, which means it believes it is very, very accurate. If you compare this to, it's even smaller than that. It's incredibly close. It's a 0.008, which means it is thinking it is extremely close to being accurate. If you go up higher, the numbers should get larger. If you go up a long way, you can roughly see it's up on 0.09 here. And when it runs 3,000 times, obviously it gets very accurate towards the end, and it sort of stabilizes at a certain amount. Maybe if I run it a few less times. If I only run it 100 times. Given I've also already run it, so it probably also be... I've already run it, so it is remembering basically its previous attempts. Okay, that's the neural networking side of my thing complete. And this is the front end. This is the double sort of look. So what we have is a symbol class which takes an image. In this case, the image is simply blue, a card, green, and red. It is taking these. It's taking off the PNG. So that's when we're printing it out. We're creating a button class. We're going to click on these. Initial those in the variables. This is the drawing of the actual. I believe this is the card, one of the cards. And this is drawing the background. This is drawing the background, which is in black. That's the color code there. This is telling us if anything is clicked. Well, this is telling us if anything's hovering over something. This is something that's clicked. Replacing a card. This function is if you match a symbol correctly, it will then replace the card on the left with your card and ensure that the card is accurate. These are currently generated randomly, the cards, which can be changed for anything in the future. The locations of the buttons are generated through this. So this is the initial generation, which is randomized. So for X and Y. And then this is all checking that the coordinates are valid. So you can't have two of the same button on top of each other. For example, if you've got red, green, blue in the bottom left, middle and right, it'll make sure that in those correct orientations and it is not 3 in the bottom left or 2 in the middle and 1 on the right. This is defining the buttons, and then we're returning all of these values. This is the main function. So we have the left buttons being declared first, and we're declaring matched as false. This is quite important. And we are generating the right hand buttons as well as the coordinates for these straight away, not in a loop, outside of the loop. This is the main while loop, which is running the drawing as well as the getting the inputs from all the button clicks and mouse clicks. This allows you to exit the program. This part of the code, if you click on the button, for example the blue button, green button, red button, this will tell you what colour you've clicked on, and it'll output a value. This is for later, telling me what's been clicked. This does this through the previous getClicked function at the top. So these are the right hand buttons telling us if they've been clicked, as the right hand is the cards that are yours and the left is the deck of cards. Here we have the left blue button. If the right blue button is clicked and then the left blue button is clicked, it will output a blue of 1, which will then mean if this is clicked, it will match the blue button, say that set blue to 0, and it will output this matched equals true. This is the same for all of these. This is loading in the cards, both of the blank cards. And here we have the match statement. When you match a card, it's set to these values as temp values, so we can use them in a second. We're going to check the coordinates. This is currently just terminal, just to check it's correct. And we're going to use this replace card function to replace the cards on the left with the cards with the positions on the right in the same orientations. However, we will solve a way to stop this right hand card being the same as before. It will always be different every time. And this is drawing the buns. I'll now run this program to show you in action. So currently we've got an exact match, so I'll match one of them, blue to blue. As you can see, we've got a new card, and the card on the right has been put on the card on the left. Now I'll repeat again. For example, red, it's matched, green, matched, blue, matched, and each time we get a new card with the card on the left being replaced by our previous card. Thank you for watching. Hope this is good.